Welcome to week 9 problem solving session. Okay, my name is Bhavya. Um I'm a PMRF fellow from IIT Madras, and we'll be having these problem solving sessions every Tuesday 6 p.m. Okay. Okay. Having said that, let's move straight to business. So previously we saw complexity. Okay, 2 weeks of complexity, right? And this time's topic. So that this is week 7 and week 8, right? So this time's topic is approximation, and it's a very nice transfer from complexity to approximation, because in complexity we just studied that there are few problems, or actually there are a lot of problems, which we shall call as NP complete or NP hard, which it is unlikely to come up that we come up with polynomial time algorithms. In fact, highly unlikely. Okay? And if someone comes up with polynomial time algorithms for NP complete problems, then we show that P equals NP. Now, and this is a notoriously difficult problem, which until now has not been solved, and it increasingly looks like this problem may not ever be resolved. Okay, so hence the difficulty of coming up with algorithms for these problems. And so what do we do? That is the question. So if we cannot get polynomial time algorithms for these problems, what can we do? And is all hope lost? That is the question, right? So it's not that all hope is lost, in a sense that practically, if you want these algorithms, then we can do pretty good. Okay, and so this is a way of coping, right, with the hardness, coping with computational hardness. And one way of coping we already saw much before, and that was using randomization. We saw that if problems are difficult, then what do? We use randomization, we toss some coins, and we realize that, oh, okay, we can solve. A good example would be, say, the algorithm for max cut, right? Kargar's algorithm. We saw randomized algorithm for max cut, and similarly, I mean, there are so many algorithms that do it, and but there is no polynomial time algorithm for max cut. And in practical scenarios, randomization is perfectly fine. For example, in looking at large databases, for example, databases of Facebook and Google, they typically use randomization because it is not possible to actually spend that much time on these data sets which are billions, trillions of bits large. Okay. So that is one way, and the other way is approximation. What is approximation? Well, you can not exactly, so I'm talking about search problems. Okay, you need not exactly get to the answer, but you will get close to the answer. That is what we have. Randomization, what is the context? Randomization says that you may not always get the correct answer, right? Approximation says that you will always get something which is close, which is approximately same as what the correct answer is. So approximation algorithms is also used all over the place, and you can actually surprisingly build very good approximation algorithms for various problems which are actually computationally very difficult to come up with deterministic algorithms. Now, before I get into approximation fully, okay, I want to solve the assignment questions. Okay, previous assignment questions. Okay, assignment 8 was the previous one, right? So, okay, some of the questions were pretty simple, so I did not put it. So which of the problems are strongly NP complete? Okay. Now recall the definition of strongly NP complete, weakly NP complete. Well, let's first define what is weakly NP complete. Okay. These are NP complete problems that have what is called a pseudo polynomial time algorithms. Okay, what do you mean by pseudo polynomial time algorithms? Their algorithm appears to be polynomial. Well, of course, since it is NP complete, we can't expect there to be a polynomial time algorithm unless P equals NP, which is not known as of now, but we already know pseudo polynomial time algorithms. What is a pseudo polynomial time algorithm? It is a polynomial time. It is an algorithm which is polynomial in one of input integers. Okay, now what do I mean by that? A good example is this is not, I'm not giving an example of weakly NP complete, I'm giving an example of pseudo polynomial, which is this Ford Fulkerson, which we saw early on the course. Ford Fulkerson, if you remember, I had mentioned that it runs in time f star times number of edges. Ford Fulkerson, what does it solve? It solves this Max-Flow problem, right? And f star times e, and here f star. Okay, here what had I said? That f star is actually a very large number. It is the flow of the maximum flow of the given network. But since this is f star and not log f star, which is the number of bits I need to represent f star, so this is the actual input size, okay, in terms of the weights of the so what is the flow? So I have a directed graph like this, right? A directed acyclic graph, and I want to know how much flow can I push. And what is f star? Well, f star is, you can take it at most to be the sum of the weights of the source or the sum of the weight of the sink. You can always take, because f star cannot be larger than that. Now each of these weights are represented in binary. So if the weights are w1, w2, w3, then it is actually represented as log w1, log w2, and log w3. Get it? So if you say f star times e, so if you say these are given in the inputs, right? The weights are given in the inputs, log w1, log w2, w3, and f star would be at most, w1 plus w2 plus w3, something like that. And if you say it is polynomial in log f star times e, then you are good, because this is the size of the input anyway. This is one of the sizes of the input anyway. But if you say f star times e, it means this is recall that a equals 2 to the log a, okay, log base 2a. So similar, using this, what do you have? We have f star is actually 2 to the log f star base 2. Okay, and if log f star is the size of the input, I mean, or the size of the weights, which is represented in binary, you are actually, by saying f star, you mean 2 to the log f star, and where log f star is input, size of input, you are actually doing exponential. So pseudo polynomial, that's why the pseudo means false, right? So it is a false polynomial. That, yeah.
So I have a query here that so similarly I can write n, simple n. N is equal to, say, 2 raised to the power log 2n, isn't it?
N is equal to 2 raised to the power log 2n. Yeah.
If I follow the same logic here also, understand what this log to n thing is. So this is the number of the bits required to represent to the number n. So in that case, every polynomial number n is an exponential number.
No. So not necessarily. It depends on what n is. So if here n, okay. So yeah, I get it. What Goel is saying is that can't I use the same logic? For example, n is a number. So n is equal to the log to the log 2n. So it is exponential in log n. Well, there is a slight confusion here, and I'm glad that Goel addressed it. It depends on what n is. If n is the size of input in terms of bits needed to represent it, then it's totally fine because it's 2 to the log n, which is not exponential on the input size because input size is already n. But if n is an integer, which is not the size of the input, but it is rather the input represented by it, which if you treat the input like a number, okay, if you treat the input like a number, then if you take n, then it becomes exponential because that number is actually represented using log n bits. A good example of this, okay, is when you test if a number is prime or not. Prime is the set of p such that p is prime, and p is an integer. The simplest algorithm for it would be, go across all d less than p, okay, d less than 1 less than d is less than p. So go across all d, okay, or this is confusing. Go across all d, all those factors, you would say, from 2 to p minus 1. So let's say input is p. You want to check whether p is a prime or not. And what do? You simply check if d divides p. Okay, check if d divides p. If yes, output yes, else continue. This is the simplest way to check whether it's a prime or not, right? This algorithm, you may think that it's polynomial. It's not a polynomial time algorithm. It's a pseudo polynomial time algorithm. Why? Let's see. What is the, okay. Can you tell me what is the running time of this algorithm? Wait.
Of the order of, so I would be checking p divisibility of p minus 1 numbers. So therefore it would be of the order of p.
It will be of the order of p. Is everyone convinced? So this is a problem. This is the most natural algorithm. The most natural algorithm to check whether it's a prime or not is go across all d, okay, which from 2 to p minus 1. Check if d divides p. If yes, then sorry. This checks compositeness. Sorry. If yes, output no. If something divides, then output no. Else continue. So here this is the loop, let's say, and here I'll say if here I'll just say output yes, right? So everyone is convinced, right, that this takes time p, order p, not p, but order p, right? Kishore, is this right? Okay, Sanjay is here, so okay. So this takes order p time, or to be exact, 2 to p minus 1 means p minus 3 or something like that. This takes order p time, and but p is the input, right? And then you will say that, oh, this is a polynomial time. P is input. So this is a polytime algorithm because I'm getting order p. But this is wrong. Claiming this is wrong. Why? Because I am not calculating. I should not calculate the running time based on the input that I'm based on the number that I'm getting. Okay, based on the number that I should be. Do not compute. Do not check runtime based on the input number. Check based on the input size, which is given in binary to you. Which is given in binary. So what is the input size? Is actually log p. Okay, so in fact this p may be confusing, so I'll write n. Input is a number n. Okay, okay, so check based on the input size, which is given in binary. So input size is log of the number that you are trying to represent. So, and the what is the running time that I saw? Okay, the running time is order n time. So run time is order n, which is order 2 to the log n. But what is log n? This is the input size.
So from this discussion, I am having an impression that while determining the execution time, we need to see that whether whatever we are getting, whether it is in terms of the count or the number itself. Like in the case of the sorting algorithm, when we say that the complexity is of the order of say, n square. So probably actually do we mean to say that there are n, count is n, and then this count ka square is the complexity of the algorithm.
Okay. That is a good point that Goel raised. So for example, when we say let's say bubble sort takes order n square time, it is acceptable, okay, because from a non-complexity point of view, from a naive algorithm's point of view, this is fine, okay. But also note why this is fine, okay. Why is this not too bad of a problem? Because the input to a sorting problem is an array, okay, and where it is 1, 2, 3, 4, and so on. Let's say till so the size of the array is n, and each of the inputs are maximum. Let's say the maximum input is m. Maximum input is m. Maximum input number, maximum element. Maximum element is m. Then it takes at most log n bits to represent each of them. So actually, when you say n square, you actually mean order. You do this log m, and you can roughly assume this to be n. Or since you will be these bubble sorting algorithms, you are thinking of running it on a RAM machine where each of them are constant, then it does not matter. So, but let's say in the worst case, you will take this to be something like log n. Whichever is bigger, you take it like that. And so the actual input size is something like n times log n. And if you take something like n square, it is still fine. It is not an exponential gap. Even if you compare merge sort, say, and if input is n, the input array size is actually n log n. If you compare something like n log n, it's still fine. Both are polynomial. But this is unacceptable. I mean, because of the details here, okay, if your input is actually of log n size and your running time is actually exponential, so this is an example of a bad algorithm.
But still, if n is the representation of the problem size in terms of the number of the bits, then how this quantity which you wrote in the previous slide, say n is equal to that equality, n is equal to 2 raised to the power log 2n, become polynomial and not the exponential. Not this one. I mean,
because see, here, okay, this is the input size.
So can you write that equality again here?
In terms of bits.
So can you write that equality again here on this slide? Say n is equal to 2 raised to the power log 2n.
N is equal to 2 raised to the power log base 2n.
Yeah. Now let us say that this n is the representation of the number in terms of the bits.
So let me call it m so that we don't get confused.
Yeah. So now say now not in this context, in general context. So let us keep it n only. And now say if n is the size of the problem in terms of the number of the bits. But then in that case also, if I write n is equal to 2 raised to the power log 2n, so that quantity log 2n would still be something, but then that would be fixed thing.
Right. So see, input size, if I do like n, okay, so this is the running time, right? N square, order n square.
Yes.
So what do I do? Order n square is equal to order 2 to the log n square. So this square I can put it at the front. So 2 to the 2 log n.
Yes.
Now I will not say that it is exponential in terms of my input because my input size is n log n, not log n.
So if the input size is n log n, and why the input size is n log n, by the way? Because we have
because there are n many cells in the array, and each of the cells has log n bits to represent.
I see. So let us say that the complexity of the algorithm is of the order of n square, and is equal to of the order of 2 raised to the power log 2n, say. Then why not this quantity in the right hand side would be the exponential one?
It is exponential in terms of 2 log n, but it is not exponential in terms of n log n, which is the input size to this problem. You get it, right? There is no factor of n here. It should be n times log n in terms of in order to be exponential in terms of the input.
Oh, I see. I understood.
But in the primes case, the input size is log n itself.
Yes.
And the algorithm running time is 2 to the log n. Okay.
I understood.
So, yeah. So therefore it is exponential.
But then still, so I will stick to that interpretation only, that while writing the runtime, we need to see that whether it is the count or is it the number itself.
So
number itself, then it is the quality of the pseudo polynomial.
So count, yeah. So I won't say count, but rather say the number represented.
So I mean, what is the issue in calling? I mean, this has the count, because this indeed is the count that
okay. So because if you say count, okay, here too n represents a sort of a count, right?
Yes.
So, but in this case, considering it as a count is not causing a problem, especially if you have something like an array, an adjacency matrix. So here too, you are talking about count. N represents the n bits. The bits, number of bits is sort of equal to the number of vertices. Sort of n square, but yeah. So rather than saying it corresponds to count, say that the decimal number represented in the decimal form, not binary form. Okay. So for example, like I said, Ford Fulkerson. In Ford Fulkerson, there is this F star, right? F star is at most the sum of the weights of the sink or the sum of the weights of the source equivalently. Now, F star is a decimal number, not a binary number. I mean, F star is in decimal representation, not the binary representation. If it was binary representation, it would be log F star.
So say instead of the F star, it could have been, say, the number of the outgoing edges from the source. So then it will be a count like the feeding, and then probably in that case the algorithm would have executed in the polynomial, isn't it?
Not the number of outgoing edges, but say the sum of the weights of the outgoing edges.
Like
Okay.
in this case, if
Oh, okay. You mean like if it was the number of outgoing edges, then it would be polynomial.
yes.
Yeah, that's true. If it is like the number of outgoing edges, it would be polynomial. Yeah, and this is an example where count is not causing the problem.
Yes.
Okay. So okay. Anyway, yeah. Okay. Good. So these are the kind of problems that are called weakly NP. Oh, so first of all, this is what is called a pseudo polynomial time algorithm. Now, you have what is a weakly NP complete? Well, it is NP complete, but it has a pseudo polynomial time algorithm. But having a pseudo polynomial time algorithms, you can see that it does not actually show a polynomial time algorithm. So it does not imply that P is equal to NP, even though that they are NP complete. Okay. Yeah. So 0 and Naxab, I'm going to come to that. Okay. But I'll address it one by one. So 3-SAT, okay, is not a pseudo polynomial time algorithm. In fact, if 3-SAT has a pseudo polynomial time algorithm, since everything reduces to 3-SAT algorithm, everything will have every algorithm. Every NP algorithm problem will have a pseudo polynomial time algorithm, and it is not so far. And a pseudo polynomial time algorithm is not known for 3-SAT. Vertex cover is another thing that strongly reduces to 3-SAT. Okay. So this also does not have a pseudo polynomial time algorithm. Before coming to partition, I'll come to knapsack. Knapsack has a pseudo polynomial time algorithm. And what is the algorithm? Well, you may have seen in your data structures design analysis algorithms course or something that knapsack problem has a pseudo polynomial. I mean, we didn't study it that way, but it has a dynamic problem programming way to do it. What is the dynamic programming? Well, it consists of remembering intermediate sub problems, the answers to that, and then combining them to come up with the answer. Okay. So well, knapsack has one. Well, the algorithm goes something like if I have. Oh, by the way, what is a knapsack problem? Knapsack problem is I have items A1, A2, and so on till AN, and each of them has a value V1, V2, and Vn, and each of them has weight W1, W2, and so on till Wn. These are items, and I have a sack, okay, of size capital W. Okay, a sack of size capital W. And here I want to put these items, maybe A1, A2. But what is the problem? I cannot put too many items. That is the sum of the items, sum of the AI in the sack, okay, is cannot be in the sack. Let me call the sack S, cannot be more than the weight of the sack, the full capacity of the sack. And of course I want to maximize the value, maximize vi, okay, such that these are the constraints. And I'm not going to do the algorithm in detail, but the algorithm is something like, if I have a knapsack, okay, and I look at the case when I have put, say n many, so I have the knapsack and it is full at a time, so ith iteration. Now I want to tell what is the most optimal way to put an item here. The most optimal way, is it some a1, a2, whatever? So I actually check if I can put a, so what do? I recursively call this process and I remove wi amount of weight and then get the optimal value for the remaining sack recursively, and then put the ai back and compute the value. And I maintain a table. This is a typical DP way to do it. I maintain a table, and then given the previous, so the recursions that happen every time I get an answer, I put it in the table, and then I can reference it. Anyhow, what I mean to say is that this takes nw time. Okay, this takes nw time, this process of using TP knapsack takes nw time. And what is n? Well, n is the number of inputs, number of items. But here what you see is w is the max weight of knapsack. W is the max weight of knapsack. And the max weight of knapsack, mind you, in the input is represented in binary.
So what is small n means?
The small n is the number of items that you need to put in the knapsack, the choices for. Okay, that is still fine. That is not causing the problem. What is causing the problem is this capital W. By problem, I mean causing the runtime to be pseudo polynomial instead of polynomial. So W is the max weight of the knapsack in the actual input. Okay, in the input I have A1 to AN, not A1 to AN, sorry, V1 to VN, W1 to WN given to me, and both in binary, and then I have capital W given to me also in binary. And if I'm given in binary, then the length is, the size of the input is log W. But here what do you have? W. But W is 2 to the log W, and log W is the input, one of the input. So this is a pseudo polynomial. You can check out the detailed algorithm in separately, but I'm not doing the algorithm in detail because this is done in a lot of standard courses. Yeah, go ahead.
So why this log to W is in terms of the problem size, because say while computing the value of the log to W, I need to count the number of the items, or is there any other reason for considering this as equivalent of the size of the problem?
I do not understand that. Yeah, what did you say? Sorry.
Yeah, so I need to say that why are we considering this log to W cumbersome or problematic? Because this log to W is representing what? Is representing the problem size.
No, it is representing the size of the knapsack.
Size of the knapsack. And why is this problematic? Size of the knapsack is problematic.
So why is the size of the knapsack problematic? Because size of the knapsack is one of the inputs given to us, right? It is a vital information. Because unless I'm given the size of the knapsack, I cannot tell how many inputs I can put.
I see. Because this is one of the input. So therefore this is creating the trouble.
Exactly. This is one of the inputs. It needs to be given as an input, because if it is not given as an input, it means W is a constant. But then my algorithm will only work for, when the knapsack is of size 100 or say 1000 or for a fixed constant. So W needs to be given as an input.
Oh, yes. So like say in this case, in a modified knapsack problem, apart from the values and the weights and the capacity of the knapsack, if a small modification is given, say number of the participants who are putting the weights into the knapsack. So, and finally say if we come up with the running time as equals to 2 raised to the power log 2 p, wherein p is the number of the participants.
Okay.
In that case, also would be considered the execution time of the modified.
Okay. So you mean n can be written as 2 to the log n times w, right? This is what you have, and you mean this is exponential?
Not this one is exponential. Say I am giving one more problem, one more input. So right now we have been given the input.
Oh, okay. So you give n. You mean that, right?
So not only this n, say p is given, wherein p is the number of the participants and who are responsible for placing the weights into the knapsack.
Number of participants who are responsible for placing. So what do you mean by participants? Who are the participants?
So participants, I mean, are responsible. They will pick the weight and put it inside the knapsack.
But the problem originally does not have this version, right? You are the only participant. I mean, the algorithm is the only participant, right?
Yes, so that is why I'm talking about the modified knapsack problem.
Okay.
From the two inputs, we have been given an additional input.
Okay.
And that additional input may not be relevant at all. But then finally, say if we come up with an algorithm, say which is of the order of say 2 raised to the power log 2 p, wherein p is the number of the participants.
Okay.
So basically, I want to confirm here that whatever, say, if the execution time is in terms of the number of the inputs, one of the input, so then also will it be considered as a problematic case, and the algorithm would be considered as a pseudo.
Yeah, well, if you give something like p here,
yeah,
and your running time has a p here,
yeah,
it is pseudo polynomial.
Yes, and even though there is no w. Say I have something.
Even if let's say there is no w, okay, and you have p here, and then you give some p here, it is pseudo polynomial.
Yes, now I understood. Yeah.
Okay, because this p here is a natural number or integer, whatever. Okay.
Yes.
So okay, great. So knapsack, and then you also, it was done in the lectures that knapsack is actually NP complete. So this has a pseudo polynomial time algorithm. Yeah, Kishore?
Yes, basically, when you say pseudo polynomial,
Yeah.
basically it doesn't take into consideration the bits of the input, right? It takes directly the number of inputs, how much we give you.
Exactly. It does not. The pseudo polynomial, the running time will not have the. I mean, it can have in other parts, but at least one of the part will have the decimal representation.
Yeah, of course, decimal representation is okay, because decimal representation also is one of the real numbers. I mean, like any maybe it's not like an integer. I'm saying a number, a natural number, probably
like a natural number or integer.
Yeah. So, but here what we are taking for the weights is the log. So when we are taking the log, right, 2 to the power of log 2 w, we are considering the bits, right?
We are considering the
bits of input.
Bits of input, right?
Then how come this comes under the category of pseudo polynomial?
So you see that it is order nw time, right?
Yeah, this is pseudo polynomial.
Why is this pseudo? Yeah, exactly. Why is this pseudo polynomial? Because I do n times 2 to the log w. This is the same thing, right? W is equal to 2 to the log w, right? Right.
Okay.
Like I said before, a is equal to 2 to the log a. This thing. Okay. So times n times 2 to the log w But what is log W? Log W is the input size, is one of the input size. As soon as so actually the input size is not W. The input size is log W.
So when we are saying, when we are trying to describe the problem, right? The A's are items, A1 to AI, and then V1 to VI are the vertices, and then W1 to WI are the what do you say, the bytes.
Weights,
So
right. So
those
these
those W1 to WI are those bits of the inputs.
okay. That's a good question. Now, what are W1 to Wn's? They are also natural numbers, right? W1 to Wn are also natural numbers. V1 to Vn are also natural numbers. They are the weights
Right.
and value, right?
Right.
But given as input in binary, they require log n bits. Okay, so not log n bits, but let's say log. So this requires what? This requires log v1 bits. This requires log vn bits. This requires log w1 bits, and this requires log wn bits. Right. Okay, so what I can simply say is this will require at least log v times, because okay, and what is v? V is the max value, and let's say if he's a, and let's say w, okay, let's call it v, x is the max weight of an item. Okay, so each of them takes at most, sorry, this should be at most, so each of them takes at most log capital V many bits to represent it, because the maximum value Vi, okay, so the maximum value, let's say Vn was the maximum, itself took log V, itself took Vn, so the others will always of course be lesser. So this will be at most log V times, each of them take capital V many bits, so log V times n plus, this is the maximum is x, so if each of them take at most x, log at most log x, okay, log x times n plus for this guy, which represents the weight of the knapsack, maximum value of the knapsack, which is log w. So this is the size of your input.
Yeah, see, this in case when you are trying to put in terms of polynomial time, right?
Yeah, now your algorithm should run in polynomial time with respect to this.
No, but the question is with respect to the pseudo polynomial time, right?
Sorry. So a polynomial time algorithm. Okay, if you want to come up with a purely polynomial time algorithm, it should run in polynomial time with respect to this.
Right.
Because this is the input.
So we should convert all the inputs in terms of log, right? And then we should evaluate so that it becomes, maybe if we get the answer, then it is a polynomial time algorithm.
If the answer is polynomial with respect to all the terms here,
right,
or polynomial with respect to this input size, this is bits. This is in terms of bits.
right, right.
If it is polynomial with respect to this, then it is a purely polynomial time.
Exactly.
But what does knapsack problem have? It has n times w. Observe that n is not causing a problem because n is the input size. N is at most the input size here. Right, and n is not causing a problem because n is not causing a problem. What do I mean by causing a problem? I mean stopping it from being a purely polynomial time algorithm. Okay, why is it not stopping? Because n is still the size of the input. I mean, still at most the size of the input. Okay, what is causing a problem here? This factor of w is causing a problem here. Why? Because the input has a log W term and the running time has 2 to the log W term. This W is actually 2 to the log W. So in terms of the input, it is exponential.
So what do you mean here? N represents the number of bytes what we are inputting. Is that
Number of items, number of total items in the knapsack. Sorry, not in the knapsack, but the choices you have, number of different types.
here in this case order of NW? It's just like n number of W's what we are inputting, right? So let us suppose n is equal to 10, then we are inputting 10 weights. Is that right?
If n is equal to 10, then it becomes 10W. That is fine. But
That's why it is not causing the problem.
You can interpret it that way also. Yeah, you can interpret it in that way also, because 10 if n is equal to 10, the input anyway had at least 10 bits. At least 10 bits. There could be more bits also, but
I would like to add something here. Say if there are n, if the value of n is 10, then this ever happen that the total weight W becomes exponential in terms of 10. See, I have been given 10 number of the objects, and the maximum value of the weight 10 can be, say, I add every weight once, right? So like say if I've been given 5 objects, so then this order of n capital W will create a problem when the weight W becomes greater than or equals to 32, because I have been given 5 number of the objects. Then only this W would be viewed as something exponential. If I
yeah.
Then the total weight should be greater than, say, 64. So, I mean, another reason of creating the difficulty here for the 0-1 knapsack problem could be that many a times it may so happen that the weight W, the total weight W, may become exponential in terms of the number of the items to be placed in the knapsack.
That is true, Goyal, but we need not analyze it that. I mean that I agree that if W goes so high, W goes so high that it goes over exponential in terms of n. Definitely, it is exponential. And but do we always reach that case? We cannot guarantee.
Sometimes we may reach to that.
Sometimes we may reach, but we may not guarantee. So that would mean that maybe there's a better analysis that shows that, oh, okay, this is not exponential. So that's why it is important that you include W as also input, and therefore W has a certain input size, which is log W, and by this analysis it shows 2 to the log W. Clearly it is exponential in one of the input parts.
Is 2 log to the power of log 2W, is it exponential or considered as exponential?
Yeah, this is considered exponential. So see, even something like anything can be considered exponential. First of all, 2 to the log, very small number can also be considered exponential. But right. What is it exponential with respect to? It is with respect to this, right? It is with respect to the power, right? So here what do you have? You have 2 to the log W. This is considered exponential with respect to log W. Right.
Yeah, that's true.
Where log W is a part of the input.
Okay, so just for my understanding's sake, let us take this way. So n multiplied with the exact value of W. Can we do that way? And let us suppose n.
Okay. N multiplied with. Hello, Kishore. Hello. I'm not able to hear you. Okay. Are others able to hear Kishore? Okay, wait, I'm not able to. Others, are you able to hear me at least?
Yes, I can hear.
Oh, okay. Then Kishore, can you hear Kishore? Goel, can you hear Kishore?
No, I cannot hear you.
Oh, okay. Probably log out and log in. One second.
So did you find any flaw in my argument that this is creating trouble? Because
So what, in your argument, you mean that, see, W could this W can be so large that W can be so large that it can exceed n. I mean, it can be exponential in it. That's what you say, no?
Yes.
Okay. Now I agree with that. Yeah, at least in this scenario, it is. Um, okay, at least in this scenario, you can say that. Okay. Yeah.
Sorry, my internet lost. So
Okay.
I have to rejoin again.
Sure, no problem. Yeah. So you were saying?
Yeah. See, instead of we are replacing W with 2 to the power of log 2 W, right?
Yeah.
So instead of that, can we directly replace W values as it is?
By as it is meaning? By the natural
See, what
number
are the values
it represents?
as inputs? Yeah, inputs.
Yeah,
That's
yeah,
the line.
it's the same thing. So it's just that these two are equal. I'm to visualize exponentiality. I'm doing this, but you can say W. Let's say the order n. See, W is not a constant. No, it's an input. But you can say for a particular case, for a particular input, let's say W is 100.
Right.
Okay, or let's say for convenience. Okay, yeah, 100. Okay, W is 100. But if you set 100 to the machine, okay, to the computer algorithm, you will not represent 100 using 100 ones, right? Or you will not represent, you won't write 100, right? Internally, it will be represented in binary.
Yeah, that's true. For the evaluation purpose, for the machine evaluation purpose, we convert it to log. That we understand because it understands
Exactly.
0 1 bit.
So your input will look like, okay, so you have some V1 to Vn, W1 to Wn, followed by the binary representation of 100, which is of how many bits long? 7 bits probably. Yeah, well, just a moment. Which is 7 bits long. So, but this is 100, and if you're this is 1000, then the input is only 10 bits long, and if you go something like 2 to the 1000 is the size of W, your input is only of size 1000 bits long. So your this is so tiny input size. It's just, I mean, 100 bits is 1000 bits is still large, but it's not too large. Okay, it's not as large as this. This is insanely large. I don't think there is a computer that can represent 2 to the 1000. You see the blow up, right? It's exponential, right? If you feed a number here, which is just 1000 bits long, which is just 1 MB in size.
Yeah, that I understand. But what my confusion is, see, even for the polynomial time evaluation, when we wanted to give the task to a machine, or even either in case of pseudo polynomial, the process or the calculation steps are same, right? So either in pseudo polynomial time evaluation, we are converting it to log, and then whereas even for the polynomial time also we are converting into log bits,
Okay.
and then we are
See,
getting.
that is why it's important to compare with respect to the input size. Okay. Yeah, I'll keep that question in mind. I'm going to address that. Yeah, Goel, you are raising your hand.
Yes, so, but then now, so my apprehension is that it is not 100 which is causing the trouble. It is because this is one of the input size that is causing the trouble. It is one of the input that is causing it.
That's right. So that's why I'm saying the W is not a constant. It can't be just be 100 or it can't just be 1000 for any input. I'm just looking at particular instances of different inputs. So when W is 100, when W is 1000, of course W is not particularly, but you are right to say that. Yeah, that's right. Whatever you say.
But then if it is right, then I can also write this n as n raised to the power 2 raised to the
I
power.
was about to say that. Okay, to address Kishore's point. Okay, so Kishore, I can write this. Okay, so to address your doubt, I can write this as 2 to the log 2n times 2 to the log 2w, right? Because a equals 2 to the log, okay, right? So I can always write n also as 2 to the log 2n, right, Kishore?
Right.
So, but why did I say that only w is causing a problem, n is not causing a problem here? Because you might say that, oh, it's 2 to the log n and it's clearly exponential in log n. Even n should be causing a problem here, right? Even this n should be causing a problem here because it's actually exponential. The reason I'm saying n is not causing a problem and saying that n is not, yeah, exactly, n is also in, because it is important to note down what is it exponential in. This term is exponential in log n, and I am interested. I am talking, saying exponential time only when it is exponential in terms of the input size. But is there the input size is n, which is much larger. It's exponentially larger than log n. So what is the input size? It is something times n log w plus w log w. Okay, but here, what do I have? 2 to the log n. If I had a log n term here and only log n terms log n, clearly n is greater than log n, right? So the input itself is greater than the input size n. Okay, so this is exponential in terms of log n, which is clearly smaller than n. In other words, okay, I don't know whether how much of convincing I did.
No. So, see, of course, when you are saying n is greater than 2 to the power of log 2n, is that the statement right?
Not n is greater than 2 to the log n. N is actually exactly equal to 2 to the log n.
Right, exactly.
So n is exactly equal to 2 to the log n. Now you might say, why is it the case that I'm not claiming n is causing this runtime to be exponential? Why is only w causing the runtime to be exponential?
Right.
Because here I have 2 to the log n. But by exponential time, I mean exponential in terms of the input size. Okay, exponential in terms of the input size. But what is the input size? This. What am I getting exponential in? Exponential in terms of log n. Here, do I see any log n term? I mean, even if there is a log n term, the input is clearly much larger than log n, no? Because n is much larger than log n.
Or in this logic, w is also larger than log 2w.
W is also, yeah. So, okay, but do you see a w here? You only see log w, right?
So in that case, see, we are considering knapsack as a pseudo polynomial time algorithm, right?
Knapsack has a pseudo polynomial time algorithm. Not
Okay.
knapsack
So
is a
it can
problem.
be also it can be also like act as an polynomial time algorithm as a problem as well.
Okay. So knapsack problem cannot have. Sorry, it's not that it cannot have a polynomial time algorithm, but it is highly unlikely that it has a polynomial time algorithm because it is an NP complete problem. So if it has a polynomial time algorithm, then P equals NP.
So, but what I based on my understanding, what I can say, it's a matter of just conversion to bits. See, if we wanted to put it in a polynomial time, right? Let us put even log of n values in bits and then like also w log of w bits as well. So that's when we convert the problem into this way, right? Probably it comes into polynomial time. So when we give n as a directly as a natural number and then w into what do you say into log bits, right? So that will be a pseudo polynomial. So
But you should have a um, algorithm that does it, right? It's not like every we don't know whether all problems are pseudo polynomial time algorithms, because
no, see, given a problem, right? Given a problem for the same problem, like let us suppose v, a, v, and then w for the same values. What I'm saying is, can we what do you say, evaluate them into polynomial term as well as pseudo
no. So why not? Okay, see, first okay, sorry. So this is one important thing. Okay, every polynomial time algorithm is still a pseudo polynomial time because it runs in less than pseudo polynomial time. But every pseudo polynomial time algorithm is not a polynomial time algorithm because it is actually running in exponential time. Okay, that much is clear, right? Yeah, go ahead.
Yes, so your explanation makes lots of sense to me when you say that this input size is less than or equals to log Vn plus log Xn and plus log W. And whatever we are getting 2 raised to the power something, and that something is log W.
Right.
That something is not log n.
It's not log n.
Yes, had there been a term of log 2n here in the right hand side while computing this input size, then this n would have created travelers.
Then the input itself is actually larger than the running time. Trivially, it becomes polynomial. That's right.
Now this is clear to me.
Okay, good. So Kishore, it's not true that I can always achieve a pseudo polynomial time algorithm. Okay, so it's so okay. Wait, I'll so poly time. Okay, wait. So poly time. Oh, what's wrong? So poly time is still a type of pseudo poly time. Okay, it's like saying this any poly time algorithm is also an exponential time algorithm. It's something like saying, because according to asymptotics it is still fine, right? Because n is at least order 2 to the n, right? This is perfectly valid to say because order notation represents an upper bound. But pseudo poly time is not poly time, not contained in poly time. Oh, this is trivially true because pseudo poly time is actually an exponential time algorithm disguised to look like a polynomial time algorithm. It is not a polynomial time algorithm. So, okay, what you are saying, Kishore, is something like this. Okay, what you said is something like you have an algorithm that has a runtime of order, say n, not n cube times m, right? Kishore, this is what you mean, and this where m is now this you can write it as order 2 to the n cube times 2 to the m. So you say that, oh, this is also a pseudo polynomial time. That's what you mean, right, Kishore? That any algorithm, regardless of whatever it is, can be made into a pseudo polynomial. Right. Or so this
is representing the numbering. That's it.
Right.
If we represent that number into exponential, then it has to be a pseudo polynomial.
No, no. This has to be 2 raised to the power log 2 and n cube and then that.
I'll come to that now. But but it depends on what the input is, Kishore. But it is still fine. Okay, this algorithm is still a pseudo polynomial time algorithm. I'll agree to that. Let's say, but something like this. Okay, order n cube times 2 to the n. Let's say, and input is of n bits. Can I convert this to pseudo polynomial type? I'll write order 2 to the n cube. Okay, fine. Times 2 to the, oh sorry, not 2 to the n cube, 2 to the, so here it will be log n cube, here log m, here, oh yeah, okay, so Goel, you were saying this, no? Sorry, okay, at that time it didn't understand. So this can be converted to 2 to the log n cube times 2 to the log.
To the log.
Is this correct?
No, it's directly to the power of
2 to
log.
the log 2 to the n.
2 to the power of log.
No, 2 to the power. No. See, 2 to the n. This entire chunk I'm trying to convert it to 2 to the log something. So it will be 2 to the log 2 to the n. Right?
Okay.
Okay, this is correct, no? Now, so what is this? This is equal to order 2 to the 3 log n times 2 to the n log 2 base 2. So this is nothing but 2 to the n. But why am I even converting it? See, now is this pseudo polynomial type? Like I said before, look at the number of bits here. Okay, here I have log n, here I have n. This expression is exponential in terms of log n. But what is my input? N. This expression is exponential in terms of log n. Or let this, by property of log, I can move 3 here. That's why I can say that this expression is exponential in terms of order log n. But what is the input size? N bits. So this is not exponential in terms of the input size, because n is clearly larger than log n. So that's why when you convert it back, it becomes n cube. N cube cannot be written in the form that is exponential in itself. That would mean n cube is equal to 2 to the n cube, which would be a ridiculous statement to make, because it shows that two totally different natural numbers are actually equal. Look at the input size and look at this. This is exponential in log n, and here the input size is n. Okay, so this is not causing a problem. As in this, this conversion is not a valid conversion. Similarly here, this conversion is not a valid conversion if, let's say, input is n plus m bits. Let's say input is n plus n bits. Then what do I have? I have that this expression is exponential in terms of log n cube, but log n cube is clearly smaller than n. So this is not exponential with respect to the input. This is also not exponential with respect to the input. because here I have log m and the input. Do you see any log m? I mean there are only terms which are it could have log m, but uh, the largest terms are like very large, n, m, and so on, much larger than log. Okay, so it's important what now look at this. Now, okay, I have 2 to the n here. Now here I have what? Already I have 2 to the n. How do I read it? I say this is exponential in terms of n. But what is the input? N bits. So this is clearly exponential in terms of the input. So this is causing a problem. So similarly, I have this here, and the runtime of that knapsack DP algorithm is order NW, capital W, and this small n can be written as 2 to the log n. I agree, but 2 to the log n, this log n is this is not n. If it was n, I would agree. If it is n, since there is factors of n here in the input size, n bits, it is exponential in n. But what do I have here? I have log n, which is exponentially smaller than n. And here I have 2 to the log w. Now I'm saying this is causing a problem because look at what it is exponential with respect to log w, which is exactly the size of the input. I mean, one of the parameters in the size of the input.
Right.
So, yeah. So, but let me know. Okay. So, I would recommend you to actually look at this prime example, this algorithm to check whether this is prime. Analyze this example, and because see, this particular n times w is a combination of several things. So, first of all, its input is distributed across different parameters. So, it gets harder to analyze. So, first look at a simple case when you are doing this prime solving. This algorithm takes order n time, where n is not the size of the input, it is the input itself, the number represent, the natural number itself.
Right.
Right. And so what do you get? Well, you get input size is log n and runtime is order n. I convert this n to 2 to the log n because I cannot directly say that this is polynomial with respect to log n because clearly they are different. I don't know how it's related. So I convert this to log n. I realize that, oh, okay, 2 to the this runtime is exponential with respect to log n, and log n is my input. So therefore, this algorithm is actually running in exponential time.
Oh, yeah. Yeah. If the input itself in log n, then it is exponential.
Right. That's right. So Goel said exponential in terms of input size or not is the key. That's right. Look at what it is exponential in. Exponential with respect. Okay. So okay. So okay, we spent a lot of time there, but I hope it was clear. Now see, the partition also has a DP problem, and there too you can see there is a partition. Okay, I forgot the exact bound that they have for the algorithm. Okay, running time, but partition also similarly has a pseudo polynomial algorithm. Okay, and it's also NP complete. And moving on, I have which of the following are strongly NP complete? Again, now this time we are asking the opposite question. Okay, not weakly NP complete, strongly NP complete, which means which of them do not have a known pseudo polynomial time algorithm. Okay, so 2SAT has a polynomial time algorithm, which means this polynomial time algorithm can also be trivially converted into pseudo polynomial time algorithm. Okay, and so 2SAT has a polynomial time algorithm, and max cut, min cut. So you may remember that min-cut has a polynomial time algorithm. There is a polynomial time algorithm to do this, and how you use this, if you remember this max flow min-cut theorem. And max cut in edge weight, this does not, we don't have known algorithm, and set cover also we do not know yet. Okay, and yeah, so this is some, did I do this last time? Okay, so anyway, subset sum vertex cover are both NP complete. So subset sum reduces to vertex cover, and vertex cover, since they are also in NP, reduces to subset sum, and subset sum polynomial time reduces to 2SAT. Now 2SAT is in P. So if you have that an NP complete language reduces to a P language, it means that you've come up with a P language for subset sum, which means that everything reduces to, and since subset sum is NP complete, so if subset sum reduces to 2SAT, it implies that subset sum is in P, and we know that subset sum is NP complete. Therefore, P will be equal to NP. So this cannot happen. And finally, 2SAT polynomial time reduces to subset sum. This is true because 2SAT is in NP. 2SAT is in P, which means that 2SAT is also in NP. And if it is in NP, and all NP problems reduces to any NP complete problem, and subset sum is NP complete, 2SAT problem reduces to subset sum. So this is true. So the answer is A, B, D. Okay. Now, a polynomial time algorithm for the decision version of 3SAT implies a polynomial time algorithm for optimization. Okay. This is something that I did in last time's session when I re-recorded the version because I could get time to do it. This has its answer in what is called the self-reducibility property. SAT or 3SAT here in this case. What is 3SAT? Well, 3SAT is given a 3CNF formula, which means it is a formula of this form, and each of it has an AND gate on top, OR gate below it, and each of the OR gate has 3 inputs. Okay, and question is this satisfiable or not? Okay, so what we can always do is, yeah, well,
So if the problem A can be reduced into the problem B, so that shows that the problem B is at least as hard as the problem A is. So now say if we do have a pseudo-polytime algorithm for the problem B, is it necessary that definitely we have a pseudo-polynomial time algorithm for the problem A as well?
Interesting. Okay, so good question that you adjusted. See, it does not mean you get a pseudo polynomial time algorithm for A also. But you may think that you are actually getting a pseudo polynomial time algorithm for A also. I'll tell you why. Because what you mean is A polynomial many times reduces to B, and B has pseudo polytime algorithm. Then will A also have pseudo polynomial time algorithm? That's what you're asking. The answer is no. Okay, why? You might say something like this. Okay, so you can argue that given a B solving machine, I can come up with an B solving algorithm. I can come up with an A solving algorithm. Okay, like this. This is what the reduction means, right? So, and this B solver is a pseudo polytime solver. And this sigma, okay, that takes in X, the input to A, runs in polytime. So polytime plus pseudo polytime would give you pseudo polytime. Naturally, that's what you would think. But remember, pseudo polytime, it is pseudo polytime with respect to one of the input parameters to B. For example, if B were the knapsack problem, A is the 3-sat problem. Let's say A is 3-sat, B is knapsack. Right, A is 3-sat, B is knapsack. Now, if if a knapsack is this, I say it runs in order NW time. And it is true that 3-sat reduces to knapsack because knapsack is NP complete and 3-sat is still in NP.
But then I can write, say I can solve 3-sat in an effort of the order of f of the NW.
What is f?
So f is some function which runs in the polynomial time and which is mapping each and every instance of the 3-sat instance into an instance of the knapsack problem.
But how do you come up with that f? Well, that f,
because this 3-sat is getting reduced into the knapsack problem. Say I have either a direct reduction or the indirect one. But since both the problems belongs to, say, had there been a reduction, say from 3-sat to the knapsack problem, so I can rephrase each and every instance of the 3-sat problem as an instance of the knapsack problem.
I get what you're trying to say, but see, that requires a proof, right? It's not very straightforward. What you mean is that this W, I'll get the suitable F here for the input to 3-sat.
So
it could be a parameter like the number of clauses, or some parameter, suitable parameter, but
not in that sense, wherein I would be mapping some characteristic of the input of the 3-sat to the characteristic of the knapsack problem, wherein I find something analogous to the weight W in the 3-sat domain.
What is that thing? How do you find it?
But then my point is straightforward. Say, since I can solve this
what your argument is that since you have a reduction, then you can get that also.
Yes.
But why should that parameter here, okay, which is say f here, that parameter here f, be exponential in terms of the input size?
So, but then my point is that let us consider this problem in reverse. Why would there be an exponential time algorithm for the 3-sat problem when this 3-sat is getting reduced into, and the complexity of the 3-sat cannot be higher than the complexity of the knapsack problem, like in this case. So if something which is more complex, something which is more difficult, can be solved in the pseudo polynomial time, and it could be pseudo in any sense, but then at least it gives a feeling of solving this problem slightly easily. So then why can't we solve this 3-sat problem slightly easily in a similar sense?
See, first of all, this going back from W to this particular F and easily characterizing it, that is not a simple task to do. You may say that such an F exists, and first question is, okay, how do you obtain that from the reduction? Okay, let's say if you somehow obtain that from the reduction by analyzing it. How do you guarantee that this particular F is actually exponential in the input size of this? Maybe it is doubly exponential or 3 times exponential to the size of the input to the 3-sat problem.
Yes.
That could always be the case, right? But I agree that this is an interesting place, and you in the next week you'll be looking at techniques that actually, it's called parameterization. Okay, and you should check out the lectures. Okay, what it does is it deals with algorithms where I am only concerned about running in exponential time with respect to a certain parameter. For example, even knapsack problem O and W is actually a parameterized algorithm. Okay, has a parameterized algorithm where the only parameter I care about is n. As long as this is polynomial, I'm done. This I'll consider it to be like a constant. Okay, so this is the kind of thing that you may see in the next time's lectures. And but you get what I'm trying to say, that this may not always exist.
Yeah, very much. Yeah, I'm fully convinced. Thanks.
Okay, great. Okay, so now what is self-reducibility of 3-SAT? Okay, so let's say 3-SAT is in P, and let's say it is in P via some algorithm A. So algorithm A, what does it do? It tells you in polynomial time whether a given 3CNF, what is a 3CNF? This kind of a formula is satisfiable or not. What does it mean satisfiable or not? It says, is there an satisfying assignment, which means is there an assignment that will make the circuit, make the formula output yes, true. Let's say there is somehow magically you come up with this. Question is finding a satisfying assignment also easy? That is the question. Is finding a satisfying assignment. First, this only talks about existence. Does a satisfying assignment exist or not? Yes or no. Question is finding also easy? Yeah.
I cannot understand question. So if 3-SAT is the element of P, and we do have an algorithm A to solve this problem in the polynomial time, then what is the question?
Now I want, so what is the problem 3-SAT? 3-SAT is a problem that says yes if there is a satisfying assignment, and no if there is no satisfying assignment. Right.
Yes.
So it shows the existence of a satisfying assignment. It does not find the satisfying assignment. It does not tell you so it's a decision problem. It's not a search problem. It does not tell you what the.
But then we discussed this thing last time, and quite a lot, that there were 3 types of the problems: decision problems, optimization problems.
Yeah. We discussed that. No.
Yes.
But we discussed that search problems are more difficult than decision problems. No.
Yes.
But in this case, for NP problems, search problem is a difficult problem. What am I saying? Search problem is as hard as decision problem. Surprisingly, for NP, if you can check if you can do the decision problem in polynomial time, you can also do search in polynomial time. This is one of the beauty of self-reducibility. I'll tell you why. Okay. So question is finding a satisfying assignment. This is the search version. No? Also easy. What do we mean by easy? Can be done in polynomial time.
But then, otherwise, without getting the solution, how would you say yes or no?
Without getting this, oh no. I treat that algorithm as a black. No, of course I don't see. I give you an example of that Euler-Tour thing once. No, Euler-Tour, without looking for an Euler-Tour, I can just look at the degrees of the vertices and tell you yes or no without coming up with a solution.
I think this discussion has come a couple of weeks back.
Yeah, Kishore, what?
This discussion has come up. We had discussed, I think so. So between the decision problem and the search problem, right?
Huh.
So which one is best? I think before finding a solution and then taking a decision or finding a solution. I think we discussed that.
Yeah. No, yeah, that's what I'm saying. We saw that search is at least as hard as decision. No, last time.
Right.
Because if I know the answer to search problem, I can answer decision problems also. But the other way around is more difficult.
Right.
But the last time we discussed that, I agree. What I'm telling you this time is, I understood that pseudo polynomial does not mean easier. This is exponential only. Yeah, actually, pseudo polynomial is just, I mean, it's not something that is very special. Also, don't give it too much of a special treatment. Also, because it's just exponential. It so happens that it looks polynomial. Yeah, good. So, see, this is what we saw, right? For any problem, what my claim is, what is the new thing that I'm talking about this session is that search problem is as hard as decision problem. It is not harder than decision problem for all NP problems.
And it is harder for which category of the problems then? In which category of the problems the search problem is usually complex than the decision problem?
Okay. Oh, I mean, you can take any thing outside NP. It's not very clear.
So which problems are there outside NP? Because I can, at the most, I can think of the problems which requires exponential amount of the time using deterministic algorithms.
Yeah. You can come up with problems that take that are exp complete or p space complete and so on. Okay. So yeah. Now, why do I say search problem is equal to decision problem? Okay. Now this is the surprising thing, and what do I mean by that? Okay. So this is the question. So 3SAT is in P. Let's say so this is, by the way, suppose. Okay. We do not know. Suppose 3SAT has a polynomial time algorithm, and remember 3SAT is a decision problem. It tells you whether there exists a satisfying assignment or not. Now I ask the decision problem. If 3SAT is in P via an algorithm A, can I also find the satisfying assignment in polynomial time? If the existence I guarantee you, can I also find the satisfying assignment in polynomial? If you give me this magical algorithm that decides yes or no, can I find the satisfying assignment? So this is clear, right? So I have an algorithm A. This takes a 3CNF phi as input. Okay. And this is able to output yes, no. If phi is satisfiable, no if phi is not satisfiable. Okay. Now I have this magical algorithm and this runs in polynomial time. This is all an assumption. Okay, we don't know if, because 3SAT is NP complete. Okay, since 3SAT is NP complete, if we actually have a polynomial time algorithm, we implies P. We would show P equals N. Now, by the way, for all NP problems, okay, if P equals NP, you can say in a sense. Okay, now you have this. Now come up with an algorithm B that takes an input phi and outputs a y such that y is a satisfying assignment. It outputs true on that way. If phi is satisfiable, of course. So you agree that this is the search version. So this is search version. This is the decision version. The decision version is called 3SAT. Okay. So, okay, I hope that is clear. Now, how do I come up with it? So let's say I have that algorithm. What is the most natural thing to do? Let's say I have this algorithm. Sorry. Oh, I need to charge. So I have this algorithm A. What is the most natural way to? So I can also, since I have this algorithm A, I can run it as a subroutine several times. I can run algorithm A again, run algorithm A again, and so on. Okay, in different types of phi. Now, given a phi, I want to come up with an algorithm that actually outputs the satisfying assignment also. So, what is the most natural way to do it? Natural way to do it is go across all y. So, for each y in 0 1 to the n, okay, or let me be more simple, for each y equals y1, y2, y3, and so on till yn, okay, where each yi is 0 1. Go across each string, go across each input for the. Now run algorithm a on that input y. Okay. Now if a says yes, which means, oh sorry, what am I saying? Okay, so what sorry. First, what do? I run algorithm A on uh, the input phi. Okay. So this is algorithm to look for satisfying assignment. Okay. And what is the input? Input is a circuit. It's a CNF, 3 CNF phi. Okay. Phi which takes in x1 to xn as its input. Now, how do I look for a satisfying assignment? I run algorithm A on phi. This says yes or no. If it says no, then there's no use in continuing because you can never find a satisfying assignment. Then output uh, something like impossible. Yes, meaning there's a satisfying assignment, we can find it. So, what is the most trivial way to do it? Well, go across all possible inputs. That is y1 to yn, where each of them are 0 1 bits. Go across all inputs and evaluate. And this process takes evaluation of formula only takes polynomial time. Evaluate uh, phi of y if uh, phi of y is true, then output that evaluation, which is the satisfying assignment. Otherwise, output. Otherwise, continue. So this is not the satisfying assignment. Otherwise, continue. Continue looking for output y and halt. So this is clear, right? This is an algorithm to find a satisfying assignment for a formula phi if it exists, right? But what is the running time? Okay, what is the running? I'll just get my charger. Please think about the running time.
So I think that the execution time would be n multiplied by 2 raised to the power n.
Okay.
Because there are 2 raised to the power n number of the possibilities. I mean, these many assignments are possible, but then to check whether this assignment is a valid one or not. So I'll have to make n number of the extra calculations. So there n into 2 raised to the power n probably would be the execution time.
Okay. Where does the n term come from?
N comes from because I would be having 2 raised to the power n number of the possible assignments, and to ensure that whether this assignment is leading to the true value or not, I need to
Okay, evaluation. Okay,
Yes.
the evaluation, right? Okay. So, so this is taking some polynomial time, because we know that algorithm A runs in polynomial time, and this guy takes 2 to the n time, and this guy takes again some polynomial on n, and other take constant time. So the answer is polynomial in n plus poly n times 2 to the n time. Okay. Yeah, good. So in other words, it takes exponential time. Now what I'm trying to say is, even though we have this algorithm that tells me whether it's satisfiable or not, it looks like it is not going to help us in actually finding the satisfying assignment, right? Because even if I don't do this process, let's say I don't check whether it exists or not, I just run this part, that is, go across each. Now if none of them satisfy, then I can none of them evaluate to true, then I can always output impossible. So even this is not the algorithm A seems to be redundant, right? But actually there is a nice way to actually there is a nice way to come up with an algorithm to look for a satisfying assignment, and this is what is called the self-reducibility property. Okay, so what is self-reducibility property? I'll tell you. So you have the input phi, and you have x1, x2, and so on till xn. What you do is run algorithm A on phi. Okay, what will it say? It will say yes, or it will say no. If it says no, there is no satisfying assignment, then output impossible, to look for a satisfying assignment. Otherwise what you do, you split it into two cases. Okay, otherwise check if phi 0 x1 x2 and so on till xn. Run A on. So what do? I set x1 to 0 and I ask, does it have a satisfying assignment? It may say yes or no. Well, if it says no, then what do? Since the algorithm said on phi, it said it's definitely satisfiable, either x should be 0 or x should be 1 for a satisfying assignment. Then what do? Then if I say run A on phi 1 x2 xn, here should be x2 x3. If I see this, then if this will definitely say yes. Why will it definitely say yes? Because on fixing x1 to 0, it said no. On fixing it to 0, it said no. It means that for the satisfying assignment should have a 1 as x1's value as 1, right? So it will definitely say yes. So what I'll do is I'll directly fix x1 to 1. So what I'll do is run a on, now fix x1 to 1 because it's definitely 1. Now fix x2 to 0, then x3 and so on till xn. And if it had said yes, okay, then we know that x1 is setting x1 to 0 is definitely one of the satisfying assignment has x1 as 0. So what do? I fix x1 to be 0 and x2 now again I fix to be 0 and so on till xn. Now let's say now again I have two cases. If it said yes, 0 0 followed by some x3 xn is satisfiable, then I'll say run a on 0 0 0 x 4 to xn, and if it said no, then I'll say then it means this was wrong. I mean, what do I mean by wrong? If this settings x2 to 0 will not give me a satisfying assignment, so I need to set x2 to 1. Run a on, and so then I have again cases yes, and here too if it said yes, then what do I fix phi to? I fix phi to 1 0 0 and so on till xn. And if it said no, then what will I do? I'll fix phi to 1 0 was wrong, so I'll do 1 here and then so on till xn, x3 till xn, and then I'll keep doing this process. So inductively what will happen is, and I'll traverse the sequence of yeses. Okay, these are just possibilities. My algorithm is still deterministic. Okay, I'll just go on and go through a sequence of yeses and land on a leaf. What will that leaf have? It'll have some combinations of zeros and ones, which is definitely a satisfying assignment. And what is the runtime of the algorithm? The runtime of the algorithm is the depth of the tree.
Of the order of n.
Yeah, exactly. Runtime of algorithm is equal to the depth of tree, and at each level, what are we doing? We are fixing one of the inputs, so which is equal to number of inputs in phi, which is equal to n, and plus some polynomial time. So it will running time. Okay, so yeah, it's better to write outright directly.
So do we have such a reduction for every problem in NP?
Exactly. But this, okay, before I get into that, is it clear? Kishore, is it clear?
Yeah.
Okay. Yes, we have this for every problem in NP. Why? Because let's say this problem was not 3-sat. Let's say it was something else. Let's say it was knapsack. Okay, knapsack is not a decision problem. Think of a decision problem. Let's say click
problem.
Click problem. So what do is I change the click problem. I use the reduction from click to 3-sat. Okay, and so I make a circuit out of it. I make a formula out of it using the reduction. Then I'll run this algorithm. It goes yes or no, right? And I keep doing this process.
Yes.
And at the end, I get a satisfying assignment. This satisfying assignment, I do the reduction from 3-sat. So I can also do another thing. At every stage, I can convert the this into an instance of. Oh, but that would not matter. Yeah, that's not required. It's not. So finally, I get a satisfying assignment, and that satisfying assignment will be the certificate for. If again using the reduction, the ulta reduction from 3 sat, 2 click. Yeah, Kishore.
Yeah, just a small clarification. See, when we said and then concluded that the runtime is order of n,
Yeah.
right? So when we go from the top of the tree, right? So this order of n will only consider the S evaluations, right? Only S evaluations.
That's right.
That is the order of n.
Sorry, I did not. Yes, evaluations.
Only S evaluation, because we may get no evaluations elsewhere, but that won't be considered into this order of n.
Very sorry. We can even go. No, not yes. It could be no also. Sorry. Could be no also. It will depend on the. So if I run it on 5, it says yes. I go here.
Right.
And let's say it said no, then I'll go here. And then let's say it said yes, then I'll go here, and it said no, I'll go here, and so on. So it could be a combination of yeses and no's. Sorry. But you see that we are not going across all the nodes. We are only going across a single path.
Right.
So because we are going across a single path, the runtime is only the time across the path, the number of layers.
Right. Only that subset of path.
That's right. That's right.
So where is the self-reducibility here?
So where is the self-reducibility here? So the 3 sat problem or a sat problem reduces to a smaller version of itself.
Oh, yes.
Okay. So that is called the self-reducibility property.
Because this term is new to me, so can you suggest some reference, to study more about this self-reducibility thing?
Yeah, sure. So, okay, so some of these things may be a bit advanced, but so there is another nice problem called the discrete log problem. You can look into it. It also has a self-reducibility feel to it. Another nice self-reducibility has an application which is there is a theorem called the Mahane's theorem. Okay, and it asks something like questions like how dense are NP complete languages? Can it be that NP languages are very sparse? What do I mean by sparse? It means there are only can I have an NP complete language where the NP complete problem where the elements there, okay, where the strings in the NP complete language are only of polynomially many based on the length. So what I mean is something like if there are for a given n length n length item in an NP complete language, there are only polynomially many such strings. Okay, I don't know how else to explain, but it just means that NP can I have an NP complete language which is very sparse, which is not very dense. Okay, loosely. That's what. And that was called the Hartmanis conjecture. And it is not disproved, but it was like 90% disproved by this theorem. Okay, and Mahane's theorem actually has a complicated proof to it, but there is a version of the proof which is by Manindra Agarwal from the same Manindra Agarwal from AKS Prime IIT, IIT Kanpur. Okay, and there is a version of this, so you can look it up, of version of Mahane's theorem proof, and this he gives a very simple proof for Mahane's theorem, and all you need to understand that proof is the self-reducibility property of SAT. The proof is so simple. It's just some 2-3 paragraphs long, and it's simple compared to most of the research papers in complexity. But yeah, you can read a bit about self-reducibility there.
Yes. And some book, some reference.
No,
from-
there are no books written on self-reducibility. It's not that huge of a concept also.
Okay.
But you can look at chapters in some complexity books. For example, you can look at Aurora Barak.
Is this given in this book, Aurora and Barak book, the self-reducibility concept?
Yeah. Self-reducibility is definitely discussed here.
Okay.
Okay. So yeah, this is what self-reducibility is, and well, there are other versions of self. It's not just that NP-complete problems have self-reducibility. There are some other classes which actually, have this nice property of self-reducibility. But NP problems are particularly interesting because of this search versus decision thing. Anyway, so before we end this session, so by this optimization version, it means the search version. Okay, optimization, I would not go with this name because it's a bad way to call search problem because you're not really optimizing anything here. So this will be true. So this means search. Okay, this will be true. Polynomial time algorithm for optimization. This is also true because this is an NP problem. Polynomial time for algorithm for every problem in PoNP. This is also true because you are saying that you have a P algorithm for NP. So this would mean that P equals NP anyway. So even the assumption was you have a 3 sat is in P, which means P equals NP. Okay. So the same thing will hold for PoNP also. And a polynomial time algorithm for every decidable problem. Now this is not true. This only the domain is only for the other problems will remain as it is. It just says that you can get search from decision. That's it.
Yes.
Okay. So okay, with that we'll end the session. I could not get into this week's one. Yeah.
Yeah. One quick clarification. Okay, can you go back to the same previous
Okay.
problem?
This one. Where?
The problem.
The
Before we have.
problem is this one.
The polynomial time for.
Oh, okay. Here. Okay.
So the problem statement is a polynomial time algorithm for the decision version of 3-sat. That means it implies a polynomial time algorithm for the search version of 3-sat.
That's right.
So if you take these two statements, does that mean that the runtime for the problem statement and an option statement is same?
Runtime for the what do you mean by problem? Oh, you mean runtime for the decision version of 3-sat and optimization.
Runtime for 3-sat.
A decision version and search version.
Runtime for the decision version of 3-sat and then the search version of 3-sat. It will be same.
They are not same, but they are both polynomial. They are. I mean, we saw right here. This is the. Okay. Sorry.
Okay.
This is not order n. This is times number of input, depth of the tree times runtime of A, which is number of input times some polynomial. So you get a linear factor, n times the decision version runtime. So this runs in time t1, this runs in time t2, then t2 is some n times t1. Okay, linear over it.
So even in case of inputs as well, right? For 3-sat decision problem, inputs will be different, and then a search version of 3-sat inputs will be different.
No, input will be same.
Input will be same.
Input will be same. So you can think of this as t2 of n is equal to n times t2 of n. Order n times because n is smaller than actually.
So in that case, the result should be also same, right?
Result should be same, meaning?
Let us suppose we got some 3-sat decision problem. We got, of course, the result will be yes or no in the decision version. but to get that decision, the algorithm will run, and then it takes some amount of time.
Huh.
The same amount of time will be also taken for the search version of 3 set. Providing the
Okay. I get it. Right. What you are saying is, yeah, you can without assuming that T1 is polynomial time. No?
no see,
Huh?
we assume that, we decided that, concluded based on the proofs, that problem statement and then option A statement are true. That's the reason we have ticked it, right?
Yeah.
So even when we get into the details, right? So the decision version of 3SAT as well as the search version of 3SAT will have different effort when we wanted to reach a solution,
Yeah,
or reach the end point.
Yeah.
So in that case, right, what my thought went was, might be the input might be bit less or more, but when you said the input is same, so the evaluation inside the when the algorithm is running, right, the effort will be same, but the output will be different for the two versions.
Yeah.
So the runtime, when we say that, when we are calculating the polynomial time, right, it should, of course, irrespective of the output, the time taken for the evaluation will be same, right? For the
Time
decision version
taken
as
for
well as,
evaluation, yeah. So for example, the self-reducibility algorithm that we saw, it was running the algorithm A over and over again, right?
Right.
So that particular evaluation will take time, that T1 say. So that's right. So if you look at the self-reducibility argument, here we are running A on 5. Again we are running A on 5. Again we are running A on 5. We are running it n times. That's why this takes what time? How much time? T2 of T1 of n or T2 of T1 of n. This takes T1 of n time. This also takes T1 of n time. How many times? Order n many times. That's why we said T2 of n is equal to order n times T1 of n. Okay.
Is it can be reversed, like T1 of n is equal to order of n, T2 of n?
T1 of n is equal to, no. That
was my question.
Oh, okay, that was your question. So do you mean that T1 of n is equal to order Tn of T2 of order n of T2 of? Oh, that is your question.
Because as per our discussion, input is same. Of course, irrespective of output, input is same. Evaluation effort will be also same.
So see here, what is T1? T1 is the search version. No.
Right.
Or is it the decision version? Search version?
No, decision version.
T1 is the decision version.
Right.
Well, yeah, this is true. Because, see, decision problem, this is a decision problem, and you are saying decision problem is takes at most order n times T2 of n. So this is true. This is trivially true, because T2 of n is anyway a harder problem. I mean, the search problem is anyway a harder problem, and plus you are giving some linear overhead to me also. Then I'm very much happy. T1 of n, because actually if you give me a T2 of n algorithm, just with now, what does T2 of n represent? The time taken by the search version.
Right.
And just give me the search version. I will run my input, which is a 3 CNF, and check, and then if my search version gives me a non-trivial output, okay, it either outputs a satisfying assignment or it says impossible, right?
Right.
If it says impossible, then I'll output a 0. That is a decision problem.
Exactly.
If it says something else, then I'll output yes.
So that is with respect to the decision.
So that is with respect to the decision. So in fact, I can say something stronger. T1 of n is equal to some constant time plus T2. I can even make it better because this this is all that I need. That T2 of, and I run the machine. If it says impossible, then I'll say output no, and if it says something else, then I'll put yes. So that will take some constant time. So I can tell something's wrong. Okay. So, and therefore this is also true. Okay. Okay. So.
So one more thing in general, the uploads what you are putting onto the site, right? So
Yeah.
the sharing location. So that will be remain till how long? Till the examination date?
YouTube videos, you mean?
YouTube and then the notes.
Yeah. That don't worry. That will stay much long after the exam also. So it will probably stay long for, I don't know, another 10 years or so.
It can be accessible. Right? It
can be accessed. Okay. And I could not do this week's. Okay, by the way, there was a mistake in the assignment. I think here the question 10, I think this should be the maximum value. But I'll raise it up with the instructor. So let's see. Okay, so I could not complete this, but this was all the notes I had made for this week's topic. So this is just a cheat sheet to remember the problem and the approximation ratio. So you can refer to this. Okay, it's okay, and this is something like that. And yeah, this take a look at this before solving this week's assignment. It may be easier. That's it. Okay. Any other questions? And I'll stop the class.
Thank you so much. This was very, very interesting session.
Oh, okay. Thank you.
Thank you so much.
Oh yeah, thank you, Kishore. Okay. Okay, I'm glad you loved the session.
Good night.
Okay, then good night. Bye.
Yeah, bye-bye.
Yeah.